All right, everyone, welcome back to AI Paper Podcasts. Today we're diving into a paper that's tackling, well, I'm sure you all know, the feeling prompt engineering, especially those really, really complex LLM workflows where, manually tweaking just takes forever. It's LLM-AutoDiff, auto-differentiate any LLM workflow. And with me is, as always, our wonderful expert.
Thanks. It's a very interesting paper. I think it has the potential to really change things for, well, anyone who works with these big, powerful, large language models. The idea at the core of it is really simple. Take the principles of, automatic differentiation, the backbone of how we train neural networks, and apply those principles to the world of text.
Okay, I'm definitely intrigued, but maybe let's take a step back for a second. You said prompt engineering is a pain point. Why is this such a big problem?
Well, even with all the amazing things LLMs can do these days, getting that perfect prompt is, well, it's still more art than science. And it gets so much harder when you're dealing with these really intricate pipelines, multiple LLMs, retrievers, data formatters, all these pieces chained together.
Yeah, okay, I see what you mean. Like when you're talking about multi-hop retrieval, agent loops, that kind of thing.
Yeah.
Manually optimizing prompts for every single stage, that sounds like a nightmare.
Exactly. It's not even just about the time it takes manual prompt engineering. It's just way too easy to make mistakes, to get things inconsistent. And it's hard to see the big picture of how your prompts are actually affecting the whole system.
Okay, so LLM-AutoDiff is saying, hey, what if we could just automate this whole process? Like take inspiration from how we train neural networks, but for prompts.
Yeah, you got it. They basically represent the entire LLM system as like a directed graph. Each node could be an LLM, it could be a functional part of the system, even a custom operation you've defined.
Hold on, so we're not just talking about optimizing the prompt for like one single LLM. We're talking about optimizing the whole chain of prompts across the entire workflow. That's a pretty big goal, right?
It is. And the big insight here is they treat every single textual input in that pipeline, every single one, as a trainable parameter. Just like, we adjust the weights of a neural network based on those gradients, LLM-AutoDiff, it wants to refine those prompts step by step using what they call textual gradients.
Okay, all right, now we're getting to the interesting part. Textual gradients. That sounds kind of magical, honestly. How do those actually work?
It all starts with that computation graph, the one we talked about. When the system does a forward pass, it goes through all those nodes, just like any LLM pipeline. But the key is it keeps track of all the inputs and outputs along the way, like really meticulously.
So it's like documenting every little bit of text that flows through the system, leaving a trail.
Exactly. Then once it gets to that final output, it checks how well it did based on whatever metric you're using. And that evaluation gets turned into a kind of like a textual loss, like you would have with, a numerical loss when you're training a regular neural network.
Got it. Okay.
Yeah.
So now we have this textual loss at the end.
Yeah.
Then what happens?
That's when we do the backward pass. That's where the magic happens. This is where those textual gradients come in. Starting from that final output, they use another LM, they call it the backward engine, to give feedback on how the output from the previous node could be better.
Okay, so it's working its way back up that graph step by step.
Yeah.
And using this backward engine LLM to suggest refinements to the text at each stage.
Exactly. And here's what's really cool, because they have that super detailed record of every input and output. The backward engine can give very specific feedback. It's not just make the output better, but given this specific input you got and this specific error further down the line, here's how you should tweak your prompt to improve things.
Wow, that's already pretty amazing. But before we get too excited, what about those functional nodes, the ones you mentioned before, the ones that don't actually have prompts you can adjust? How do those fit in?
That's a great question. And it's a big challenge for any system trying to optimize these LLM workflows, right? I mean, the point is to optimize the whole pipeline, not just the LLMs themselves. LLM-AutoDiff, they tackle this using pass-through gradients.
Pass-through gradients. So we're just ignoring those functional nodes then?
Not exactly. It's more like recognizing that those nodes, they're important, but they don't directly change the text. So those gradients, they just kind of pass through those nodes, carrying the feedback back to the closest LLM node that actually does have a prompt we can tweak.
Oh, that makes sense. It's like saying, hey, Retriever, the problem might not be with you, but maybe the LLM that gave you that query could do a better job.
Yeah, exactly. And because we have that record of everything that happened during the forward pass, that backward engine can pinpoint exactly which LLM needs its prompt adjusted to help the retriever do its job better.
Okay, I think I'm starting to get it now. But I have a feeling this is just the tip of the iceberg for what LLM-AutoDiff can do, right? What other clever tricks do they have to make this work?
Oh, there's a lot more to unpack. That's exactly what we'll be diving into next. So one of the things that really impressed me about this paper is how they deal with cycles in these workflows. Think about, like multi-hop reasoning or those agent-based systems where you might call the same LLM component multiple times in like one single execution.
Right, like a chatbot that has to like go back and forth between clarifying what the user wants and then, actually retrieving information based on that clarified request.
Exactly. In those situations, you can end up with multiple gradients for the same node. Each one is like feedback from a different part of the loop. And it's super important to keep track of those and apply them in the right order. Otherwise, you might get these like conflicting updates that just make things worse.
Okay, yeah, I see what you mean. So how does LLM-AutoDiff make sure those gradients are applied in the right way?
They have this really neat concept of what they call time-sequential gradients. So basically, each time a node gets called, it gets a timestamp. And then the gradients that go with that specific call, they get tagged with that timestamp too. So that way they're applied in the correct order, like chronologically. It makes sure there's no confusion about which feedback goes with which step in the process.
Oh, that's clever. It's like having a detailed log of every step, so you can trace back exactly how each prompt contributed to the final result.
And it gets even more granular than that. Remember how we talked about like prompts often having multiple parts, like instructions, a few examples, how the output should be formatted, all that stuff bundled together.
Yeah. I mean, it's pretty rare these days to just have one line of text as a prompt.
Right. Well, LLM-AutoDiff actually treats those different parts as like separate peer nodes in the graph.
Oh, interesting. So instead of treating the whole prompt as one big chunk, they're splitting it up. Does that actually make a big difference?
Oh, it makes a huge difference. If you just look at the whole prompt, it's really hard to know which part is causing problems. But when you split them up like that, the backward engine can give much more specific feedback. It might say, hey, the instructions are fine, but those examples you gave are misleading, or that output format is messing things up later on.
Ah, okay, that makes sense. So it's like having a team of like specialists, each one focused on a different part of the prompt.
Exactly. And this really granular feedback, it also helps the prompt optimizer, the LLM that's actually generating those improved prompts based on the backward engine's suggestions. By seeing which parts of the prompt are working and which aren't, the optimizer can make smarter updates.
Okay, this is all super impressive. But honestly, I have to ask, isn't this incredibly computationally expensive? We're talking about running multiple LLMs, maybe for like tons of iterations, keeping track of all this text data.
It's a valid concern. The authors of the paper, they knew this was a potential issue, so they came up with some really clever ways to make LLM-AutoDiff more efficient. One of the coolest is what they call selective gradient computation.
Selective gradient computation.
Yeah.
Okay, that sounds interesting. Tell me more.
Basically, the idea is instead of calculating gradients for every single example in your training data, you just focus on the ones where the system is messing up.
So if the system is already doing well on certain examples, no need to waste time trying to make those prompts even better. Yeah, I can see how that makes sense.
Exactly. It's all about focusing your resources where they're actually needed. By zeroing in on those error cases, you not only speed up the training, but you also make sure that backward engine is mostly looking at situations where improvements are actually needed.
That's pretty smart. What other tricks do they use to make things more efficient?
Well, they also use a two-stage validation process. When the prompt optimizer comes up with a new prompt, it first gets tested on just a small part of the data, like a mini batch. And only if it actually shows improvement on that mini batch does it then get tested on the full validation set.
So it's kind of like a quick check before they commit to a more thorough evaluation. I can see how that would save a lot of time, especially as your data set gets bigger and bigger.
Absolutely. They even have a way to generate multiple prompt candidates in a single backward pass, almost like a beam search. That way they can explore different options without having to go through that whole backward pass each time, which streamlines things even further.
So it sounds like they've really thought about how to make this whole system as efficient as possible. But what about the prompt optimizer itself? You mentioned earlier that they're building on some previous work, specifically OPRO, right? Optimization by prompting.
Yeah, they've taken OPRO and added some really nice improvements to make it even better in this, auto differentiation setting. They call it the gradient-driven prompt optimizer, or GDPO. One key improvement is adding an extended proposal history.
Proposal history. So the optimizer is keeping track of which prompts have been tried before and how well they did.
Yes. But it's not just like a list of good and bad prompts. It's a detailed record of how each prompt was changed, like the reasoning behind those changes, and whether those changes actually helped or not. That gives the optimizer a lot more context to work with, which helps it avoid making the same mistakes and make better decisions.
It's almost like the optimizer itself is learning, from experience.
Yeah.
That's really interesting. This brings up another question, though. How does LLM-AutoDiff deal with situations where your workflow has, lots of interconnected components?
You're talking about what they call system awareness, right? In those really complex pipelines, it's not enough for the optimizer to just focus on individual prompts. It needs to understand how those prompts interact with each other and with all the other parts of the system.
Yeah, so it's not just about optimizing each prompt in isolation, but optimizing the whole system, recognizing that those prompts are all part of this, bigger interconnected network.
Exactly. They do this by giving the optimizer what they call metadata about each prompt's role in the system. So that way, the optimizer can make decisions that are better for the whole system, making sure the prompts it generates not only work well on their own, but also play nicely with everything else.
Wow, this is seriously impressive stuff.
Yeah.
But maybe let's shift gears a bit and talk about how all of this actually works in practice. The authors ran experiments on different tasks to see how well LLM-AutoDiff performs. What did they find?
So they tested it on 5 different types of pipelines, from simple single LLM tasks to those really complex multi-hop retrieval and agent-based workflows. And what they found was that LLM-AutoDiff consistently beat traditional prompt engineering methods across the board, even TextGrad, which was the state of the art before this.
Okay, so they're claiming some big improvements. Can you give me some specific examples of the tasks they used and the results they got?
Sure. Let's start with a simple one. It's called object count. It's a question answering task where the LLM has to count the number of objects of a certain type in a picture, like how many red apples are in this image.
So it's testing how well the LLM can understand and reason about visual information?
Right. Which is normal prompt engineering, they got an accuracy of 78%. But with LLM-AutoDiff, they got that up to 95%. And that was after just 12 training steps. That shows you how quickly this method can find those effective prompts.
Wow, that's a huge difference. What about a more complex task, something that really puts those multi-component capabilities to the test?
They tried LLM-AutoDiff on different versions of retrieval augmented generation, or AG, pipelines using the Hotpot QA dataset. This dataset is designed for multi-hop question answering, so the system has to put together information from multiple sources to answer the question.
Okay, so you've got multiple LLMs involved, plus those retriever components that all need to work together.
Exactly. And they tested everything from a basic 2-component Aura grid setup to a much more complicated, what they call agentic RAG pipeline that uses a React-style agent with multiple tools.
And how did LLM-AutoDiff do in these more difficult setups? Did it live up to, all the hype?
It definitely did. They saw big improvements in accuracy across the board compared to both manual prompt engineering and those other automatic approaches. And maybe even more importantly, they found that LLM-AutoDiff was way more efficient in terms of both time and, how many tokens it used.
So it's not just about better results, it's about getting those results faster and with less computational overhead.
Exactly. And all of that efficiency, it comes directly from those optimizations we talked about. The selective gradient computation, the 2-stage validation, and the ability to try out multiple prompt candidates at once.
Okay, so we've covered a lot of ground here. We've talked about why LLM-AutoDiff was created, how it actually works, how it handles those really complex scenarios, how it stays efficient, and even some really promising results from their experiments. I think our listeners have a good idea of what this system is all about now.
I agree. We've given them a good overview of how the system is structured and what it can do. But of course, no research paper is perfect, right? There are always limitations and questions that still need to be addressed.
That's true. No system can do everything perfectly. What are some of the challenges or open questions that come up with this research? What should we be thinking about going forward?
Well, that's exactly what we'll be diving into next. So one thing to remember is that this paper is really focused on prompt engineering, right? LLM-AutoDiff, it's amazing at optimizing those textual prompts. But what about all the other things that go into an LLM pipeline? Things like hyperparameters or the model architecture, even deciding which LLM is best for a specific task.
Yeah, those are important points. It would be incredible if we could automate those things too, right? Imagine being able to just tweak all those settings
Right.
automatically.
Oh, definitely. That's one of the really exciting things this research opens up. Like, how can we take this idea of textual auto-differentiation and use it for those other elements? Can we make a unified framework that looks at prompts, hyperparameters, maybe even model architectures, all as part of one big optimization space? That would be a huge step forward.
Yeah, I'd love to see that. Another thing I'm curious about is the data. We know that the quality and amount of training data is super important for any machine learning, right? How does LM-AutoDiff handle that?
That's a really important point. Just like any machine learning technique, the success of LLM-AutoDiff really depends on having good training data. And with LLMs, that usually means having labeled data with, high-quality examples and clear ways to measure performance. One really interesting area for future research is how can we use LLMs themselves to help label data or maybe even create synthetic training data?
Using LLMs to train other LLMs. That's a cool idea, like a self-bootstrapping kind of thing.
Yeah.
Okay, last thing I'm wondering about, how does LLM-AutoDiff deal with dynamic graphs? Like graphs that change, especially in agent-based systems where the structure of that pipeline might change over time as the agent learns and adapts.
Yeah, that's a really interesting challenge. It's actually something the authors mention as an area for future work. Think about an agent that, learns to use new tools or develops more sophisticated reasoning strategies. That agent's workflow, the graph that represents it, would need to change too, right?
Exactly. So how do we make LLM-AutoDiff flexible enough to handle those kinds of evolving workflows?
That's the big question. Maybe it means developing ways to add or remove nodes in the graph dynamically, or maybe even letting the agent suggest changes to its own workflow, based on what it's learning. There's a lot of room for innovation there.
Okay, one more big question that I can't ignore integrating this with, model fine-tuning. We've been talking about optimizing prompts and how those pipelines are structured, but what if we could combine the power of textual auto-differentiation with actually fine-tuning the LLM weights themselves?
Oh yeah, you're talking about the holy grail now. Imagine a system where we're optimizing the prompts, the structure of the pipeline, and the actual model weights all at the same time, all working together to get the best possible performance.
It's almost like blurring the lines between prompt engineering and actual model training. Is that even possible?
It's a tough problem, but I don't think it's impossible. There are already some cool approaches out there that combine prompt optimization with things like parameter-efficient fine-tuning. The hard part is finding the right balance, making sure those different optimization processes work well together and don't interfere with each other.
Well, this has been a really fascinating deep dive into LLM-AutoDiff. It's clear that this research could totally change the way we build and use LLM applications. It's amazing to see these kinds of innovations coming out, really pushing the boundaries of what's possible with language models.
Absolutely. LLM-AutoDiff is a big step towards making LLMs easier to use, more efficient, and just more powerful. And it's only the beginning, I'm so excited to see where this research goes next.
And to our listeners, if you want to learn more about LM-AutoDiff, definitely check out the full paper. The authors did a great job explaining the concepts and showing what the system can do. And who knows, maybe you'll get inspired to build on this work and help create the next big breakthrough in ALAO.
Absolutely. The future of LLMs is bright, and it's being shaped by people like you, researchers and engineers out there. Keep exploring, keep innovating, keep pushing the boundaries. That's what makes this field so exciting and rewarding.
I couldn't have said it better myself.
Yeah.
And with that, we'll wrap up this deep dive into LLM-AutoDiff. Until next time, happy prompting.